Okay, this is part 2 of the practice problems for the Chapter 7 test on 2D forces. Yet another symmetrical sign hanging problem. All right, this is starting to become quite the snoozer. All I'm doing is I'm just solving for something different. I'm just using my same setup, same thing. I just have a different variable. This time I'm trying to solve for theta. Yet another one. This is only applicable. I don't mind you memorizing and using this so long as that you always recall that this is only applicable if I am symmetrical. Okay, another symmetrical sign hanging problem. I'm solving for theta, and I need that angle theta. Once you got this, that's the physics. The rest is geometry. Okay, I'm trying to find out this height. How low is the sign below the ceiling? So actually, I'm really trying to just solve this little triangle right here for this side opposite, right? Yeah, side opposite. Yeah. All right, so I got this angle because that is the direction that the tension has to go. Where did I get this 1 meter from? Well, if that's 4 meters and that's 2 meters, then this overhanging portion of the trapezoid has to be 1 meter per side. And like I said, we really have a geometry problem here, and we come up for this side opposite. All right, this is how we really do business on sign hanging problems. Not symmetrical. So this step becomes critical. When you see this, you know that you're going to have to solve simultaneous equations. My favorite way to do it is by substitution. So it's also easier to start off looking at your equilibrium in this direction first. Okay, so the horizontal component of this vector and the horizontal component of that vector must equal each other. That's this statement here. I went ahead and I solved this for one of my variables. You could have solved it for T2 just as easy as T1, doesn't matter. But I'm going to need this statement for a substitution into my other equation that I developed for my equilibrium in this direction. And this is my equilibrium statement, force canceling each other out in this direction. The y component of this plus the y component of that minus the y component of that has to equal 0. Right here is where I do my algebraic substitution, combine like terms, and solve. Now I think maybe on yours I had reversed T1 and T2. All right, but the process is the same. Now I take that and I can back calculate. Actually, I do think this is reversed. T1 should have the higher force in it. I mean T2. Okay, there we go. All right, common problem is when we look at this geometric diagram, a lot of times students will say, well, there's no way the x component of this and the x component of that cancel out. Clearly, they're a different length. Speaking of their geometry and your distances, you're correct. Speaking of the forces, you're incorrect. The only relationship between this diagram and your force diagram is these angles, these directions. These hypotenuse can be totally different and often always are. So you need to remember that. A force diagram and or what we call a free body diagram and just the geometry of the situation are two different things. And students often have trouble with suspension or cable suspension problem because they don't make that disconnection. The only thing I get from this geometry is the angle of my forces. It tells me nothing about their magnitude. All right, so be very careful considering that when you're working these problems. All right, last one. Okay, since this is frictionless, that makes it awful easy. The best way to kind of wrap your mind around these types of pulley problems is to look at this as a free body diagram. All right, what is motivating this force? What is causing this thing to move? Well, it's the force of gravity of this guy. Notice that they gave me weight and not mass. Okay? So in this two-block system, the only force that is acting to accelerate this system is the tug on this rope due to the weight of this mass right here. So when I do a free body diagram of the whole system, this 8 newtons weight of this has to overcome the inertia of both blocks. So this is the mass of the first block plus the mass of the second block is equal to F net times acceleration. All right, so I've got an F net of 8 newtons. There's my mass of my first block. There is the mass of my second block. There is the acceleration of the system. So I'm going to solve for A. Okay, now once I do that, we often say, okay, now what's the tension in the rope? And here's where people make a lot of mistakes. They want to say this, and this. They're equal. That's wrong. This guy has to be smaller than this if we already determined it's accelerating in this direction. So this vector, this force of tension, must be smaller. So we're going to set up Newton's second law. I could do it for this mass, or I could do it for this mass, either one. Once I know the acceleration, then I can say, let's say this guy right here, I have a force of tension. This diagram calls it Ft1, acting in this direction. And then I've got an 8 newtons acting in the opposite direction. So what does that really mean? I have to subtract those two vectors. And then that is going to be equal to my mass times my acceleration that I calculated previously. The acceleration is that direction. So since motion is that direction, we should probably call this term positive, this term positive, this term negative. Solve for that guy. All right, good luck. Master these problems.